This is a revision video about the GCSE Physics topic of momentum, which comes up in Unit 5, the forces topic of the AQA GCSE Physics or Combined Science courses. By the end of this video, you should be able to define momentum and calculate it from mass and velocity, relate the concept of momentum to stationary objects, explain what is meant by the law of conservation of momentum, and complete calculations involving collisions and explosions. We're not going to go into the interaction between momentum and forces, which links into the safety features of cars and things. That gets its own separate video later. It's easy to calculate a numerical value for momentum, but what actually is it? You can think of momentum as unstoppability or oomph. We can define it as the tendency of an object to keep moving in the same direction. So the harder it is to stop an object once it's moving, the more momentum it has. There are two things that will influence the amount of momentum that an object has. Heavier objects, like this lorry here, have a lot of momentum, and so therefore it's harder to slow them down. That's why lorries have to have much better brakes than cars. The other factor that influences how much momentum an object has is its velocity. Faster objects have more momentum. So this speeding bullet, even though it's quite small and has quite a light mass, because it's travelling so quickly, has a lot of momentum. If you can remember that heavy objects have a lot of momentum and fast objects have a lot of momentum, then actually calculating momentum is really straightforward, because the equation is momentum is mass times velocity. So all you're doing is taking the heaviness and taking the quickness and multiplying them together. In terms of units, you already know that mass is measured in kilograms and velocity is measured in meters per second. And then momentum is one of those great quantities where the units for momentum are made out of the units for the other two. So if you already know that mass is in kilograms and velocity is in meters per second, and you're going to multiply them together, well, momentum is measured in kilogram meters per second, kgm/s. So you've literally just times kg by meters per second. Let's do some practice substituting some values into this equation. Remember, your mass and velocity must be expressed in SI units. So if the mass is not in kilograms or the velocity is not in meters per second, then you need to convert before you can do the calculation. Let's look at question 1. A 60 kilogram boy is running at 8 meters per second. Now, the question hasn't told me which one of those is mass and which one of those is velocity. So what I need to do is to look at the units and they will tell me. So kilograms are the units for mass, and that tells me that 60 should go where I've written mass, and meters per second are the units for velocity, and so 8 needs to go where I've written velocity. Now I can see that momentum is 60 times 8, so I multiply those numbers together and get an answer of 480 kilogram meters per second. Pause the video and do the other 9 calculations yourself. Hopefully for question 2, you've done 700 multiplied by 30 to get an answer of 21,000 kilogram meters per second. For question 3, you've got 675 kilogram meters per second. For question 4, you've got 3 kilogram meters per second. For question 5, you've got 48 kilogram meters per second. For question 6, you've got 15. And then it gets a little bit trickier because we come to some questions where the mass or the velocity are not expressed as their SI units. So a 350 gram rock is 0.35 kilograms. You convert from grams to kilograms by dividing by 1,000. So that gives me a momentum of 0.14 kilogram meters per second. And then my 50 gram snail, again, I need to convert that to kilograms first by dividing by 1,000. And then also its velocity has been expressed in centimeters per second. So there are 100 centimeters in a meter, and therefore I need to divide this answer by 100 before I can do my calculation. So I get 0.05 times 0.02 gives me 0.001 kilogram meters per second. Sometimes, particularly at the very start of a question about momentum, you'll be asked how much momentum a stationary object has. So here's a stationary object, it's a sheep. How much momentum does it have? Well, without doing a calculation, I can tell you it will have 0 kilogram meters per second of momentum, because stationary objects don't have any momentum. Remember, momentum is the tendency of a moving object to keep moving in the same direction. Well, this object is not moving, so it has no tendency to keep moving. And so without doing a calculation, you can always say that a stationary object has zero momentum. In order for us to use momentum to make predictions about how an object is going to move in the future, we need to understand something called the conservation of momentum. Depending on the order that you've studied the GCSE science course in, you might have already met the idea of conservation of energy or mass or matter, but if you haven't, don't worry. Conservation means staying the same or nothing changing. So for all of these concepts, what conservation means is that at the end of our scenario, we'll have the same amount of momentum or matter or energy that we had at the start. We can express this by saying that in a closed system, momentum is conserved, or in other words, the total momentum before an event is the same as after the event. If you haven't studied those other laws of conservation, then you might be wondering what a closed system means. It just means that over the course of the event, no matter and no energy gets in or out. So we're not introducing anything and we're not taking anything away. We finish with what we start with. We can use the law of conservation of momentum to make predictions about collisions and explosions, although be aware that when we say explosions, this doesn't just mean bombs, it's just the term we use to describe objects moving apart from each other. Let's look at an example of a question. We've got two friends who are out roller skating. Friend number 1 weighs 75 kilograms and she's skating at 4.2 meters per second. Friend number 2 has stopped and is stationary until friend number 1 skates along and crashes into her. Now we know already that friend number 2 has no momentum because she's not moving, and we've just said from our example with the sheep that stationary objects don't have any momentum at all. We can also calculate how much momentum friend number 1 had. 75 times by 4.2 would give us 315 kilogram meters per second of momentum. So we can also say that all of the momentum in the system is 315 because I've done 315 plus 0. Now if I know that that's the amount of momentum at the start, that must also be the amount of momentum at the end. So I can use this to predict after the crash how fast will the two friends be moving, because they're not going to stop dead, they're on roller skates, they're going to carry on moving a little bit. So if friend number 2 weighs 65 kilograms, then the total mass of the two friends together is 140. Now we have to have the same amount of momentum at the end as at the start. So we've still got 315 kilogram meters per second of momentum. Only now it's split between the two friends, not just friend number 1. So 315 kilogram meters per second must be 140 kilos times by their new velocity. If I divide 315 by 140, I can now work out that they are moving at 2.25 meters per second. If I think about it, that does sound like a reasonable number. They're still moving, but they're now moving at a slower velocity than the original friend was, because there's more mass to move. Here's another example. A 5,000 kilogram lorry is travelling at 20 metres per second. Meanwhile, a 50 kilogram sheep is stationary. The lorry crashes into the sheep, and I want to know after the crash, how fast will they be moving? Firstly, I need to work out how much momentum there is at the start. I know that the sheep doesn't have any momentum because it's stationary. But the lorry starts with 100,000 kilogram meters per second of momentum. And now that momentum is going to be split between it and the sheep. To stop my slide from getting too crowded, I've turned this into a quick table instead. At the start of my scenario, the sheep had a mass of 50 kilograms. It wasn't moving and so it had no momentum. The lorry had a mass of 5,000 kilograms and it was travelling at 20 meters per second. So it has a momentum of 5,000 times 20, which is 100,000. Because of the law of conservation of momentum, I know that the momentum at the end must be the same as at the start, so it's still 100,000. I can use this to work out how quickly the lorry and the sheep together will move after the crash. Firstly, I need to think about what their total mass is. So 5,000 plus 50 is 5,050. Now I know that momentum is mass times by velocity. So 5,050 times by something is 100,000. If I do 100,000 divided by 5,050, I can work out that their new velocity is 19.8. And again, that's a logical number. The lorry's going to slow down a little bit when it hits the sheep, but not hugely. Time for you to do some practice. Can you calculate the final velocity when a 40 kilogram girl who is running at 6 meters per second collides with each of these objects? We'll do the first one together. So to start with, she collides with a 10 kilogram dog, and all of these objects are stationary, by the way. We're keeping it straightforward for now. So my first step is to work out how much momentum is there at the start of the scenario. If she weighs 40 kilograms and she's running at 6 meters per second, then she has momentum of 240 kilogram meters per second. All of my objects are stationary, so actually they're all zero and I don't need to include them in a calculation. At the end of the scenario, the total mass is her mass of 40 plus the 10 kilograms of the dog, which makes 50 kilograms. So I can now work out the velocity of the girl and the dog together by dividing 240 by 50, and that gives me a final answer of 4.8 meters per second. Pause the video and have a go at the following 5 questions. Hopefully the first 4 of these weren't too challenging for you because we've already done some of the work in the worked example. So we can carry on using the idea about the amount of momentum that the girl starts with, but now we're just going to need to change the masses that are involved. So when she crashes into the porcupine, I don't know why it was a porcupine, I just googled animals that weigh about 20 kilograms, then there's a total mass of 60, so 240 divided by 60 is 4 meters per second. If she collides with her twin, who is also exactly 40 kilograms, then they will have a velocity of 3 meters a second. A 110 kilogram moped will have a total mass of 150, so that gives us a velocity of 1.6, and the 160 kilogram bear will have a velocity of 1.2 meters per second. And these are all assuming that when she collides with the object, the two kind of almost merge together and function as one. We know that in reality, this isn't exactly how it's going to happen, but it's a good model for making predictions. Now the final question is more of a challenge, because in this one, we need to think about how quickly the man is moving and how much momentum he has. Now, you may have already picked up on this because I've been calculating momentum using velocity, not using speed. But just in case you hadn't, let's be explicit about this. Momentum is a vector, which means it has both a magnitude and a direction, and that direction will be important. If an object is moving in the opposite direction, then the momentum is not exactly the same. We need to take that direction into account. The way that we do this is by using positive and negative numbers. So in exactly the same way that if you were running at 5 meters a second in one direction and then you turned and ran at 5 meters a second in the opposite direction, we would signify that with a negative number. We do the same thing with momentum. If I have a 65 kilogram woman running at 5 meters a second to the right, I could describe her as having 325 kilogram meters per second of momentum. But if she then ran to the left, I would express this with a negative number. It's not that right and left are fundamentally positive and negative. You can decide which direction you want to be positive. But if something is moving in the opposite direction, then its momentum needs to be a negative number. So let's look back at our challenge question. We've got this 80 kilogram man and he's running in the opposite direction to the girl at 2 meters per second. So 2 meters a second is really his speed. If we're going to express his velocity, then we should take account of the fact he's running in the opposite direction. So his velocity is minus 2 meters per second. That means when I calculate his momentum, I'm going to do 80 times minus 2 and get minus 160. So whereas in the previous examples we had stationary objects and so we worked out the girl and then we just added on 0, here we need to add on minus 160. So we've said already that the girl has a momentum of 240 kilogram meters per second, and if we add minus 160 to that, we get 80 kilogram meters per second. So now we need to split that momentum between the 40 kilogram girl and the 80 kilogram man. Together they weigh 120 kilograms, so 80 divided by 120 will give a final velocity of 0.67 meters per second. Now that we can do calculations for collisions, we need to look at explosions. And as we've already said, an explosion isn't just a bomb going off, it's any scenario where I have a large object splitting apart into smaller pieces that move away from each other. Or it could be a group of objects that then breaks up. Now for GCSE, we are only going to look at scenarios where one object breaks into two pieces and they move in opposite directions. Nothing more complicated than that. In the vast majority of these questions, we're going to start from everything being stationary. So if you look at my bomb here at the start, before it explodes, it has no momentum because it's not moving. Now you might be thinking, well, how is that going to work? Because when the explosion happens, if half the bomb moves left and half the bomb moves right, both of those pieces are moving, they both have momentum, but we've said that the momentum at the end has to be 0. So what you need to remember for these questions is that momentum is a vector. Direction matters. So my piece going left and my piece going right, even if they have the same mass and they move at the same speed, they don't have the same momentum. The one going to the left might be positive and the one going to the right might be negative. And so if their values are the same, say they're both 50, well 50 and minus 50 join up together to make 0. And that's how these calculations are going to work. Let's look at this in practice. We'll go back to our friends who are roller skating. And they're maybe standing palm to palm and they're going to push off each other and see how quickly they can move away from each other. My first friend still weighs 75 kilograms and this time she's going to move 13 meters per second. My second friend still weighs 65 kilograms and I want to know how quickly she will move. So the first thing I do is work out the momentum for the object I know, friend number 1. 75 multiplied by 13 is 975. Now in order for my total momentum in the system to stay the same, friend 2 must have momentum that is the same size but the opposite sign, minus 975. So 65 multiplied by something is minus 975. And I can rearrange this to work out minus 975 divided by 65 gives me a velocity of 15 meters per second. And that makes sense. Friend number 2 is slightly lighter, so she's moving slightly faster. These explosion questions sound really complicated, but once you've had a practice of a few of them, you start to see how it works. So we have a 10 kilogram bomb that explodes and splits into two pieces, and in each question you're given the mass and the velocity of one of the pieces. You need to work out the mass of the other piece yourself because you know that the total bomb is 10 kilograms. And to start with, the bomb is stationary, so it has no momentum. So remember, the left piece and the right piece will have momentum that is the same size, the same magnitude, but the sign for the second side will be different. Let's look at a worked example together. Our first piece has a mass of 4 kilograms and it moves at 126 meters per second. Therefore, it has momentum of 504 kilogram meters per second. In order for my total momentum to still be 0, the other piece of the bomb must have minus 504 kilogram meters per second of momentum. That number is made up of the mass of that other piece, which is 6 kilograms, because the whole bomb is 10, so 10 take 4 is 6, times by the velocity. So 6 times something is minus 504, minus 504 divided by 6 is minus 84 meters per second. So that is the velocity of the second piece of the bomb. And again, do a little common sense check. Well, my second piece of the bomb is 50% heavier, so it's going a little bit slower as a result. Pause the video and have a go at the other 5 questions yourself. For each one of these questions, you need to work out the momentum of the left-hand piece and then divide that by the mass of the right-hand piece to work out the new velocity. So, a 7 kilogram piece of the bomb moving at 14.4 meters per second has 100.8 kilogram meters per second of momentum. So then the right-hand piece will have minus 100.8 kilogram meters per second, and we're going to divide it by 3 because 10 take away 7 is 3, and that gives us minus 33.6 meters per second. You should then get minus 45 for question 2, minus 9 for question 3, minus 20 for question 4, and minus 120 for question 5. All of your final answers should be negative numbers. Thank you very much for watching, and I hope that you found that a useful introduction to what is a pretty tricky concept with some tough calculations thrown in. These do get easier the more that you practice them, so I would really recommend spending some time doing some more calculations yourself. If you did find this useful, then don't forget to like and subscribe below for more GCSE Physics videos coming soon.